Welcome group to this part 2 of present value of an annuity. For this lesson I'm going to go through the investigate, which is found in your textbook 456, 457, go through those 4 questions and then also show some modeled examples of some practice problems on your student worksheet for you to be able to see this in action. I would encourage you, of course, to read through the text, and the examples shown there also are useful, and they uses extensively the TVM solver, and I'll try to work that in as well. So in this investigate, we have $1,000 per month living expenses that are needed for the next 20 years. And they're going to try to finance this. So Owen and Anna are the individuals here. And the first few questions we're asked just have to do with some of the sort of the minor details here. In 1A, we're asked how many withdrawals have Owen and Anna planned for. Well, 20 years at 12 times per year is going to be 240 withdrawals. So that's the number of $1,000 values that are needed to be withdrawn. Now, if we take that and multiply it by $1,000, that would be 240,000. That's the amount in total that they're withdrawing. The question asks here, do Owen and Anna need to have this much in their life savings account on the day they retire? So their retirement plan has them investing upon retirement a certain amount that will see them through to the end of their projected retirement years. Well, $240,000 is just the total withdrawn over those 20 years. If it's invested, there will be interest. So no, interest will reduce the amount that needs to be invested. We'll just call that the present value, okay? In other words, a lower value invested now would be able to provide $240,000 over time. Suppose Owen and Anna retire at the end of December. They will make their first withdrawal from their life savings account at the end of January. Determine the present value of this first withdrawal. So as we did before, just to reinforce this, present value for our compound interest formula requires us to take the future value and divide by 1 plus I to the n. This is just using the compound interest formula, which also in a different form resembles this. So if we're calculating that, let's see what is necessary for them to make that first withdrawal. So of course we get a value less than $1,000. I calculated off to the side here the monthly term interest rate based on 9% annual. $992.56 is the present value. So here at the end of December, that amount is invested, and at the end of January, 1 month later, it amounts to $1,000 with interest. Now, if we were to continue to calculate the present values, if we look at the second withdrawal would be made at the end of February. And of course, the money still needs to be there at the end of December. However, the amount has twice as long to compound, so the present value for the second withdrawal would be $1,000 still in the future, where the monthly rate compounds twice, and that will give us a lower value, we'll see. And of course it does. And even within a month of extra investing, we're already reducing our present value necessary to generate that by almost $7. So here, over long periods of time, present value has the ability to generate large sums without necessarily a very large investment. Key though to remember is that this $985 is also invested at the end of December. So the initial startup for the investment all the money needs to be there. We're just looking at different sums, each invested individually, to produce the individual withdrawals. Of course, the present value of an annuity question, at some point we're going to look at the total of all these withdrawals. All right, now the third withdrawal, of course, in 2D would be even smaller than that, and without calculating the value, the third withdrawal would simply be 1,000 in the future divided by 3 compounding periods at 0.75% monthly, and that will certainly be even less than, yes, the present value for the third withdrawal will be less than the present value for the second withdrawal, which we saw, which was less than the present value for the first withdrawal. And question 3 in the investigate asks, will the pattern of present values observed in step 2 continue? Of course it will. The exponent on the denominator just keeps getting larger and larger. It started at 1 for 1 month of compounding, 2, 3, and it'll just keep increasing as we go through the 20 years, which means that the amount needed to generate the very last withdrawal at the end of those 20 years would be the smallest of all, and it would have been reduced by the same factor as all the ones leading up to that. So a method to determine the sum of the present values, we've already seen this because these values are almost identical in form, except the denominator is a factor of 1.0075 greater. It would be quite easy to generate the terms, and we could really see that present value 1, we could call it, times 1 over 1.0075 will be equal to present value 2. And present value 2, if we were to simply multiply it by the reciprocal of 1.0075, that would up the exponent in the denominator there. That would give us the present value 3, and so on. So that pattern would continue all the way down to, present value 239 times 1 over 1.0075 equals present value 240. So if we have these terms all linked by a common ratio, then clearly this is a geometric sequence. And if it's a geometric sequence, we can use the sum of a geometric series to total these values. And this, of course, is the method that we used before, which is why the present value of an annuity formula looks very similar in form to the future value of an annuity. They're both totaled. All those individual principles are totaled using the formula that we know by now for geometric series as follows. So that has been already demonstrated in the previous video. Let's move on to some practice examples at this time. So from your student worksheet, question number 3 I pulled first because this asks us to calculate the regular payment. So how much does she need to deposit into an annuity that pays 6% per year, compounded monthly, to make the remaining payments? How much does she save by doing this? Let me retract that statement. The regular payment is provided here. So this is a finance question. So a loan is a good application for present value. The loan would be the present value money borrowed. And in this case, the vehicle would be the value borrowed. However, since it's 0% financing, all she's paying off is the principal, but she's paying it off in such a way that her investment makes the payments for her. Okay, so the investment creates these $920 amounts. So you would need quite a lot of money invested to generate 48 $920 payments. We know that the total payout would be 48 times 920, but the present value will be less than that, as we saw before. You don't need $1,000 invested now to generate $1,000 in the future. So let's look at the situation here. In part A, we have to figure out the present value. So our formula here is PV equals R, 1 subtract 1 plus I to the negative n, all over I. Now with this formula, there's potential for lots of error, so I would show the calculation in steps. A negative exponent has the effect of making a number smaller. So you would think that, multiplying 1.005 48 times would make it bigger, but because it's a negative exponent, it's actually the reciprocal power. And so when we subtract that from 1, I show the intermediate step, the 1.005 to the negative 48 is this number here. That's leaving us with a small number multiplied by 920, and then divided by 0.005 gives us the 39,173.89. So this is a good strategy. If you have 0% financing, it means you don't pay anything to the company to buy the vehicle, but you still need to make the payments. And rather than paying the full amount up front, if you could finance it at 0%, then all you need to do is put in the investment value, which is certainly going to be much less than the value that you actually owe. What she actually owes is 920 times 48, but the compounding power of this present value will produce those $48,920 payments. So what we're looking at here in part B is how much does she save? Well, she saves, as we see here, the total payments made, this is the power of her investment, would be the 48 times 920. That gives us a much larger value, okay, of 44,160. So her present value is certainly less than that, which means that the savings on her vehicle payment would essentially be equal to NR subtract PV. This is a little bit like looking at the interest that she earned. That's another way of thinking of it, is that's the interest that she earned on her investment. The present value was invested once but generated 48 payments. So we just take the difference between that and the present value, and we see that her investment made for her $4,986.11. So that's her savings, because she didn't have to pay that extra amount. Her investment did it for her. Let's solve this identical problem using the TVM solver. So we turn it on. Apps Finance TVM solvers number 1. We have 48 compounding periods, 48 payments, 6% annual interest rate. The 6%, there we go. Present value we don't know, so just leave it as 0. The payment, of course, is what the investment is generating, so it's a positive amount of 920. The future value will be 0. At the very last payment, the vehicle will have been paid off. The payments per year is 12, and compounding per year is also 12. So now let's go solve for the present value. Alpha solve, and we get the amount 39,173.89. So again, that's a negative value because that's money out of her pocket invested into the bank, but it will come back to her with interest. Okay, number 4 I selected as well. This is a question that requires us to determine the regular payment. Specifically underline how much can JC draw out of the annuity each month. So now we're looking at the regular payment or withdrawal that is generated from this present value. The inheritance would be the present value, assuming it's all invested. That's at $250,000. And that investment is made at an interest rate of 6.4% annually. The compounding frequency is 12. So we have a term or monthly interest rate of 6.4% divided by 12 to calculate. And we have the number of compounding periods also as necessary, which is 30 years at 12 times per year. So that's easy. That's 360 compounding periods and our monthly interest rate, we're going to calculate at 6.4%, gives us 0.0053 repeat. So it's very similar to our 6% earlier, just a little bit higher. Okay, so this is done off to the side, and this sets up the problem for us to work from the formula that we've developed. As you start to use this, you'll quickly, I hope, memorize this formula. Notice the difference in the order. The future value of an annuity formula has the 1 plus I to the end first, subtract 1, but other than that, they're identical. Now, looking at putting in our values here, well, we want to sort of follow the approach that we did earlier with the arrow diagram. To get from present value to R, we saw that we had to take the present value and multiply by I, and then we had to divide by the 1, subtract 1 plus I to the negative n. So those were the steps, if you recall, that gives us the regular deposit or regular payment or regular withdrawal from the investment. So going back to our question here, this is what we're going to do. We're going to take PV times I and divide it by 1 subtract 1 plus I to the negative n. That'll generate the regular payment, and we can calculate that with the substituted values. So we find from the calculations showing our steps that $1,564 nearly can be withdrawn every month for the next 30 years. Okay, one more technology application here, just to run this the numbers through the TVM solver. We have 360 payments at an annual rate of 6.4%. The present value is our initial principal inherited value of 250K. The payment in this case is not known, so we'll leave that blank. The future value shrinks to 0. Again, for future value questions, that always grow to a future value from nothing, and present value starts large, and eventually the money is completely depleted or the loan is completely paid off. Payments and compounding per year is both at 12. Ordinary simple annuity has the withdrawals made at the end of the compounding period, and we're just left to calculate the payment from this. So if we remember, the 250 is an investment, so it's a negative value, and that will allow us to, doesn't like that, let's make that negative, there we go, and let's calculate the payment. So alpha solve that, and we're looking for just confirmation 1563.76. Perfect. Although the question does not ask, I'll just reinforce this, that for present value questions, the interest is calculated always by taking the number of regular payments or withdrawals and subtracting the present value. And remember, the way to keep present value questions straight is that present value investments are smaller than the total value that they're worth. So the total is always NR, and the present value would be smaller, so subtract those, we'll get the interest. In a future value question, future value builds from multiple investments, and so if we want to determine the interest earned, we would subtract the contributions, or what we have looked at as total deposits. So in that case, this is larger. So here, just simply taking our $360, in this case, 360 payments of 1563.76, and subtracting off the initial principal of 250,000 will give us the interest earned. In this case, it's quite large, and be very surprised to see that it's actually more than the initial value of the investment. And this is something that we really want to share with the the student body at IFSS through a financial literacy project that by investing early, compound interest can accumulate. Someone else is doing something with the money. That's their business. That's for their purposes. But when we invest money, it can work for us. And quite clearly, this is a huge amount. It even exceeds the present value itself. So it's a real benefit. And 30 years is a long time, but really, once you start an investment, time flies when you're having fun making money. So we'll conclude the video with those two examples. You have now the challenge of wrapping this up before the end of the term so that you can be prepared to participate in the financial literacy project. And just a reminder to be submitting regularly your feedback questions, which are the achievement checks. The one for this section can be found on 463. And I think you've had a good exposure to financial applications, and it also connects well with sequences and series. So look forward to working with the group and sharing this with the student body at our school. Take care.